Hey, engineering folks. Let me get to the slides. Oh, and I never set the title slide. Hello, welcome to Lorem Ipsum Sit Dolor Emet. This is a long story. I'm moving forward. We're going to talk today a little bit about law of economy, and I'd asked in class, has anybody ever heard of Occam's razor before? I don't know where I first heard of it. I know it's come up a lot in a lot of different kinds of conversations, but basically, this is a problem-solving principle. The guy who we attribute it to, why it's called Occam's, is because William of Occam used it a lot, but a lot of people have used it a lot, so it's kind of everywhere. Notice that word economy, and think back to the visual analysis we did, where one of the sections was economy. Like, are there any extra parts, or is it all kind of everything's there? It's simple, it's minimal, everything's there it needs to be, but nothing extra. And that's kind of what this is as well. This is about not just the visual look of it, but also the function. Essentially, the simplest solution is often the best solution. So if you have two competing solutions or products or items, and you say, okay, what are my design requirements? They both meet the design requirements. If they both perform the desired function, you're going to look and see which one is simpler and choose the simpler design. Then at that point, you take your simpler design, you say, okay, is this element necessary? Is this element extraneous? Does this contribute to the function or the performance of the item? And if it doesn't, you can eliminate it. And that makes it as simple as possible. This was kind of one of your bell work questions today, was when have you compared two competing solutions? I do it all the time if I'm shopping for something. If I'm going to go buy a carpet cleaner, for example. I've done this recently, and I've had to go look, do I need one that can clean pet stains out of the rug, or do I just need a regular sort of simpler carpet cleaner? What do I actually need? And then once I figure out what I need, I'm like, well, do I need something that has all this extra stuff with that I don't, what do I need? Make it simple. One thing that I have for y'all to do is to calculate what's called the complexity factor. And this is a way of quantifying kind of how economical, in this sense, your design is. So what you're going to do is you're going to count up the number, add up the number of all the total parts in your product. So if your product has a bunch of repeated parts, you have to add every single one of those as well. Sometimes on your parts list, you'll have a certain type of screw, and you'll have 20 of those, and then you'll have a certain type of maybe dowel here, and you'll have 5 of those. Maybe you'll have 8 pieces of the same size piece of wood, If you have repeated items, you've got to add those all up. Then you have to find the total number of interfaces between the different parts of the product. An interface is where two parts come together. They can come together stuck together like a fasten. They could be a slide, it could be a rotate, it could be a cylindrical, it could be any sort of way that they come together with each other. And then there's a formula, and the formula takes a square root of the product of those two values. And that'll tell you the complexity factor. It'll give you a number, and you can compare the two with this number instead of just saying, okay, this guy's got 10 parts and this guy's got 11 parts, and well, they're really close. Maybe one of them has more things that have to fit together nicely. Here is a screenshot of this. It's kind of, I should have retyped it in Word or something, because I can make it look better than this. I just sort of zoomed it in so you could see it. Complexity factor. This symbol, that's a square root symbol. And then in parentheses, you have this sigma NP. And then you have another set of parentheses with a sigma NI in it. And when two things are parentheses next to each other, that means you multiply those two quantities together. So you have the square root of, and then inside your square root is the product of these two values. And this sigma looks like a weird E. It's a capital sigma, it's a Greek letter. It's analogous to our S. And it means the sum or the total of all of these things. So when they're actually using sum NP as one variable, which is the sum of the number of parts. And why do they say the sum of the number? Well, you might have in a part list 7 different parts, but you may have several repeated, and then you'll have 30 total parts if you count that there's 5 of these and 2 of these and 1 of these. You count up all those numbers, add them all together. And then the second one, this is the sum of the number of interfaces. So what's this look like when we're comparing products? Let me get out of this. Let me make myself larger so you can see. No, don't do that. I was going to show you a picture. This is a picture of a staple remover. And this staple remover has like a top plastic piece, a bottom plastic piece, and a metal piece right here. And if I had one in person, I could probably flip it over and see if there are any rivets or anything holding it together. So you count up the parts of this guy. 1, 2, 3. I'm assuming there's 2 rivets. You can't see them. Pretend there are 2 rivets. That's 5 parts. Something like this guy here. And you can see me up in the corner. This is the kind of staple remover most of us have, like as an office supply kind of thing. Looks kind of like a little critter. It's got wide jaws and narrow jaws, and you pinch and pull. That's basically what this does, pinch and pull. This one here, the one in the picture, that one you slide under the staple and like lift it out. All right. So let's say I was comparing staple removers together. What similarities do I notice? Well, they've both got metal parts and plastic parts. Metal for pulling the staple, and the plastic for the handles. Their functions are pretty similar. Let's do the similarities here. So the similarities, both have a part that slides under the flat of the staple, and the user then pulls upwards. Okay, how are they different? Visual differences. Well, this one is less sleek, perhaps, and it's got more symmetry. I mean, there's obviously functional things. It's kind of all wrapped up in one. The functional and visual are kind of wrapped up for me when I think about it. Visual differences I notice are that one is longer. The slide one is longer. The jaws one is shorter. What else do I notice? I notice that the slide is more sleek, and the jaws one is smaller. What operational differences do I notice? Well, I've got to, there is a hinge and a spring in the Jaws version. Let's see. There are fewer moving parts. There are no moving parts on the slide version. I could go on and on. I'm one of those people I can find thousands of things to say, so I'm going to quit. I'm going to stop while I'm ahead. And here's a little note about calculate the complexity factor. So Cummins Incorporated developed a metric for determining how complex a product design is, known as a complexity factor. And here's your values and your sums. So write the total number of each type, the parts in each type of staple remover. So I'm going to have maybe one for, whoa, why did it just go away completely? I wanted to go down. Okay. The Jaws version and the slide version. All right. So I was looking at the slide version, and the slide version appears to have, the 2 different chunks of plastic, 1 metal piece here, and I'm assuming it's got 2 rivets on the bottom because how will it hold together otherwise? So, go back to it. So that's what I'm going to say. I'm going to say, look, it's got 2 pieces of plastic, 2 rivets, and a metal tab of some sort. So it's got 5 parts. Oh, it's gone off the page now. Here, let me move this stuff up out of the way. I'm going to make this whole top section small so that it fits on one page. There we go. All right. Meanwhile, when we talk about interfaces, interfaces. My assumption is that there'd be one rivet that goes through both parts over here. So the rivet touches the top plastic piece and the bottom plastic piece. There's a location over here. If there's a second rivet down here, there's one that touches the bottom plastic piece, it touches the top plastic piece, and it touches that metal tongue there, the told still. The two plastic pieces are touching each other, and this metal piece touches the top plastic piece and the bottom plastic piece. Is there anything I'm forgetting? If that metal piece goes all the way through, then that rivet at the back is also going to hold on to it, but I'm assuming a lot already, so I'm just going to go with my eight different interfaces. Alrighty, my little JAWS guy here. Oof. I've got there's a hinge here, and the hinge is made up of a rivet, and there's a spring in here. That's why it holds itself open and it resists you pushing it closed. So there's two parts. There are two metal pieces. That's the upper jaws and lower jaws. There appears to be some sort of a I can't see it on this one. There's two plastic pieces. There's a handle on the top and on the bottom. That's 6. And on the one in the example, there actually were 4 rivets beyond that. So I'm going to go with one in the example because there were the rivets on the top here holding this plastic piece on and on the bottom. So I'm going to add the 4 rivets. There are 10 parts on this JAWS one. All right, so those 10 parts. Each of my 4 rivets touches both the plastic piece it's going through and the metal piece it's going through. So that's up to 8 already. Each of the plastic pieces touches one of the metal jaws. That's 10 interfaces. There's that rivet in the back that goes through, so I'm at 10. I haven't got any more fingers. It's got the rivet going through the first metal piece and the second metal piece, and it goes through each of them twice. So I'm going to count that as 4, and it goes through the spring. So that's 5 interfaces just from this rivet going through all those spots. And then the spring also touches, it's got 2 loose ends that touch the 2 jaws, so that's 2 more. So that's 17. I think that's all 17. Oh, each of the jaws touch each other in 2 places, so that's 18, 19. 19 interfaces. When you think about interfaces, why are they important when you're making an assembly? If I need things to fit together, then those interfaces must be, like, if I make something too big, then it's not going to fit together right. If I make something too small, it's not going to fit together right. If it's not the right shape, it's not going to fit together right. You need to make sure your interfaces match up. So you need a certain degree of precision. And that's going to make the assembling and the manufacturing more complicated. So that's why we worry about the interfaces. Alright, so let's calculate using the formula. Here, let me make this smaller too so I can see what I'm doing. Home. There we go. Okay, so the complexity factor uses the formula above. I'm going to smallerize that as well. That's a technical term, by the way, smallerize. It's late, I'm sorry, I'm a little rambly. Okay, the square root of, all it's saying is the square root of 10 times 19. So what's the square root of 10 times 19? Footer, how do I get in there? So, you know what I'm going to do, because I like to write things in equations. I'm going to use the equation editor to show you what it'll look like. Equation, that's not an option. Alright, so the JAWS one is going to be, where's my, there they are. The square roots under the radicals, so I'm going to get the normal one, square root of, and inside I'm going to have my number of parts, which was 10, and my number of interfaces, 10 times 19. So I'm going to go through, I'm going to say, okay, what's 10 times 19? It's 190. I take the square root of that. I might need a calculator. You know what? Google does just fine. Square root of 10 times 19. That's 13.78. I'm going to round it to there, 13.78. So this is, oops, it's the square root of 190. Oh, lordy, why did I get there? I keep touching the trackpad, I think. And that equals approximately. See if I push things and it hits it twice. I don't know why. What did I say it was? 13.78. 13.78. Okay, and that's the JAWS version. Alright, let's look at the slide version. Can I make it smaller? Let's look at the slide version. The slide version, we're going to have square root of 5 parts times 8. 5 parts times 8 interfaces. 5 times 8 is 40, so square root of 40. Alright, square root of 40 is going to be between 6 and 7. Clear. Square root of 40 is 6.32. And that is the slide one. Alright, so which one's more complicated? It's hopefully kind of obvious just from looking at the number of parts and interfaces that this guy that's more common, I think, more people have this type, is the more complicated of the two styles of staple removers. So that's really the little activity that I had planned for today. The version of this paper I have is about 2 types of pencils. So you're going to be looking at our trusty Papermate clear 0.7 tenths of a millimeter lead sized, this guy. And you're going to compare it to your standard kind of yellow wooden pencil with the eraser. What I'm going to do is I'm going to go put up a picture of all the parts of one of these guys. I wish I had not thrown out, I had one that was broken, and I wish I'd broken it farther and saved it and shown you all the inner workings, because if you think about all the parts, I mean, we took it apart into a certain number of individual pieces, but parts like this entire cylinder here, I think when I took, even if I took this off, I think this has, why won't it open up? I don't know. There we go. This piece, even without the button on, I think there are at least 10 parts in here, just in here. And part of it's the chuck at the front here. There are 3 metal pieces that come together. There's a ring that goes around them. There's a metal piece behind them that pushes them forward. There's a spring behind that. So that's 1, 2, 3, 4, 5, 6 with a spring. And then there are 2 separate plastic pieces. The white plastic piece is actually 2 pieces. So that's 2 more. And then there's the clear cylinderish piece, and then 1 more if you count this little rubber grip piece that's stuck on. That is 10 parts in here. And I had a student who'd broken theirs, and so we could actually see all the little bits in here, which is really cool. I think it's nifty to see how things are put together. And I will try to take a picture and have all the parts, and I'll try to give them names that we can sort of consistently use from here on out, and I'll put that in a spreadsheet. It'll be linked in this assignment somewhere. Alrighty, guys. Your job then is to do this thing. Well, the comparison to, you don't have to make it smaller. I just did that so it would all be on one page. I tried, it didn't fit. So yeah, and then you get the number of parts, the number of interfaces, and then do this little bit of math, tiny bit of math. Alrighty, you'll have a blank version of this to work with. And if you have any questions, let me know. I'm going to sign off for now so I can load this online and get it started for you. Alright, y'all take care.